In this video, we are going to look at some of the problems based on spring, vibrations and waves. So here in the first problem, a student plots a graph of load against extension as shown below and is asking you what is the spring constant of the spring. The graph is plotted for load and extension. Load is in Newton and extension is in centimeter. So to find the spring constant, we have to use the slope of the graph, which is given by y2 minus y1 over x2 minus x1. Let's take the 2 points on the plot line, one at the origin because that will make our points 0, 0. One of the points will be 0, 0 and one at the end of the plot line, which will give us 10 and 50. So let's put the numbers into the equation. So 10 minus 0, that is y2 minus y1, over 50 minus 0, that is x2 minus x1. We can calculate this and we can get the answer as 0.2 and put the units. Check what is extension plotted in. It's in centimeter, so it should be Newton per centimeter. Now if you want to find it in SI units, we should be converting centimeter to meter. So when you put the value 50, we'll write it as 0.5 because 50 centimeter is 0.5 meters. Then we get the answer for K as 20 Newton per meter. In the same graph, if the question is asking you to calculate the potential energy stored in the spring, if it is stretched by 30 centimeter, then we will take a triangle till 30 centimeter as the base. Okay, so that's important. So what they have asked is till 30 centimeters, so we'll take it till 30 centimeter. And potential energy can be found by area under graph, which is half times base times height. The base is 30 centimeter, we'll convert that into meter, which is 0.3 times the height is 6. We put that into our calculator, we get the answer as 0.9 joules. Let's look at another problem. A spring of original length 0.10 meter stretches to a new length of 0.15 meter when a block of weight 100 Newton is attached to it as shown below. It's asking us what is the extension of the spring. So extension is new length minus the original length. A new length is 0.15, the original length was 0.10, so we get that as 0.05 meter. It's asking then to find the spring constant. We can write the Hooke's law, F equal negative kx. So K will be F over x. We'll ignore the negative because spring constant is always positive. It's a constant value for a spring. We have got the force, that is a weight, as 100 Newton. So 100 divided by 0.05, we get that as 2000 Newton per meter. Another problem on spring block system. This is a horizontal spring block system. A spring block system is put into motion by pulling the block P till it reaches point A and released from rest. The block undergoes simple harmonic motion as it oscillates between points A and C to the point B. The total mechanical energy of the spring block system is 50 joules. They are asking us what are the elastic potential energy and kinetic energy at point B. So at point B, if you look at the diagram carefully, the spring is relaxed, but it's in motion because you have already started the oscillatory motion. That means if spring is relaxed at point B, elastic potential energy should be equal to 0. Mechanical energy remains constant, we know that. Mechanical energy is equal to kinetic energy plus EPE. So mechanical energy, they gave us 50, which is equal to KE plus 0 because EPE at B is 0. So we get kinetic energy as 50 joules. Now another type of question which comes in the topic of vibration and waves is about simple pendulum. How long a simple pendulum be to have a period of 2.3 seconds on the moon where G is equal to 1.6 Newton per kg. That's a formula for time period of a simple pendulum. We have got the value for time period 2.3 and G is 1.6. Now we can use shift solve on the calculator and get the answer for L, which is 0.21 meter. In case if you are using squaring methods on both the sides, then you can also do it step by step. Do not forget that we have to square on both the sides to get rid of the square root. but we can use the calculator directly and get the answer as 0.21 meter. Now on waves, there is another problem which comes with graph. So here we have got a graph between displacement and time. Question is asking us what is the frequency of the wave. So one wave is one crest and one trough. So we can find what's the time period as labeled in the diagram. We can see that time period is 4 seconds. Frequency is 1 over time period, so 1 over 4, which is 0.25 hertz. Next, we have got a periodic wave traveling to the right in a steel spring attached to the wall. So we can see that this is a real diagram of a wave. It's not a graph. The spring is steel spring is being moved up and down. It's asking us to find the amplitude and wavelength. So for amplitude, we know that it's the maximum displacement from the equilibrium position as labeled by the red arrow. That's our amplitude. Now amplitude will be equal to 0.8 over 2. As shown in the diagram, we can see that 0.8 is from the crest till the trough. So we have to do half of it, which is 0.4 meter. Now for wavelength, we have to see where is our one wave. As labeled, one wave is one crest and one trough. Then we have half a wave more. That means 1.5 wave is 4.5 meter as labeled in the diagram. Wavelength is a length for one wave. So we want it for one wave. We can get that by dividing 4.5 by 1.5. That's equal to 3 meter. Next, it tells us the wave speed is 60 meter per second. What is the frequency? We will use the wave equation, substitute the numbers into that, use our calculator. We get the answer as 20 hertz. That's straightforward. Next, a string of length 0.16 meter is stretched between two fixed ends. Draw a fourth harmonic for the string. So fourth harmonic means we should have got we should be drawing 4 loops on the diagram as shown. Then it's asking you state the number of nodes and antinodes. So I've labeled the nodes. 1, 2, 3, 4, 5 nodes are there. And then antinodes where it is having maximum amplitude. That's also labeled. So we have got 4 of them. So 4 antinodes. Calculate the distance between two consecutive antinodes. So the formula is lambda over 2 for two consecutive antinodes. But we don't know what's the wavelength. If you see the next question, it's asking calculate the wavelength of the standing wave. So let's first calculate the wavelength. Now for wavelength, we need to know what's the length of one wave. The total length of the string is given as 0.16 meter. And we know that there are 2 waves in this length of the string. So that means for one wave, it should be half of 0.16, which is 0.08 meter. So now we have got the wavelength. We can put that in part C and get what's the distance between two consecutive antinodes. That is lambda over 2, 0.08 over 2, that is 0.04. The third harmonic of a guitar string as shown below has a frequency of 240 Hz and the speed of the waves on the string is 120 meter per second. What is the distance labeled in the diagram? That is distance between two consecutive nodes. Now third harmonic and frequency and the wave speed is given to us. So let's write down the wave equation and get the wavelength first. And d is the distance between two consecutive nodes, which is half of a wave. That means it's half of the wavelength, which is 0.5 over 2, which is 0.25 meter. Okay, so let's stop here for this video.